Okay, so this is going to be lecture 5.1. I know I've already done 5.1 in class in person, but since I have extra time now, because I can make this lecture as long as I need to, I'm going to revisit some of the big ideas from 5.1. I'm going to go into detail about the difference between relative versus absolute, what this actually means. I'll draw a lot of pictures there. I'm going to kind of review how we find potential extrema, and then I'm going to get into the first derivative test, because one of the big issues with this section is not just finding the potential extrema, but then classifying them as max, min, relative, and absolute. And this test is going to help with that, because initially what we had to do is test the points around these potential extrema, and that's a lot of work. This is still going to be a lot of work, the first derivative test, but it's a little bit better. So we're going to walk through all that, and then I'm going to do a bunch of examples using everything that we've learned. I'll do examples algebraically. I'll do examples with graphs. I'm going to do as many examples as I can. Okay. So relative versus absolute. Okay, so what I'm going to do here is just draw some pictures of what it means to be a relative max or min versus an absolute max or min. So if you feel like you already have these ideas down and you feel strong about them, then you can skip this part. Okay, let's say I have some picture, some graph like this. So I've got some section of some curve, some function. I know that I'm going to have some points of interest here, some relative and absolute max and mins, and I want to show you how we're going to classify these points. So first of all, this point here, we would call an absolute minimum. We could even call it an absolute endpoint, because it's at an endpoint, an absolute endpoint minimum. Why is it an absolute endpoint minimum? It's absolute because it is lower than every other point in the graph. It's lower than every other point in this graph, in this picture, because it's got a restricted domain. It looks like if I let this function keep going, there would be lower points, at least it looks like there would be. But this function, I've cut off its domain. I've got a restricted domain here. This is, just by looking at it, this is the lowest point. This has the lowest height out of this entire picture. Thus, this is an absolute minimum. And we can say, if we're being really specific, we can say it's an absolute endpoint minimum. This point right here would be a relative interior minimum. A relative interior minimum. Interior because it's inside of the domain, it's not at an endpoint, so it's interior. It's a relative minimum because it is lower. It's not lower than every other point. Excuse me, it's not lower than every other point in this picture, right? There are surely points over here that are lower than this point, but relative to the points around it, it's lower. So I'm going to say because it is lower than the points around. If I drew a picture of this blown up, if I drew a picture of this, here's the point. There's the little neighborhood of points around this point, and the curve is something like that. It's a bit exaggerated, but that gets the point across that this is the lowest point relative to the points immediately around it. I can't say that this is the lowest point in the whole picture because once I expand this circle to these points over here, now these points are lower. That's why it's just a relative minimum. Similarly, in a similar way, this could be or would be a relative interior maximum. And this would be an absolute endpoint maximum. So this is a relative maximum because this point is higher. If I blow this picture up, this point is higher than all the other points around it, immediately around it. It's not higher overall in the whole picture, right? That's this point. That's why this point is an absolute maximum. And this point is just a relative maximum. And if we're being really specific, I can call it a relative interior maximum because it's inside of the domain, whereas this one is at an endpoint, so it's an absolute endpoint maximum. Okay, so absolute max and min do not have to be at endpoints, so let me just draw an example of that. I don't want to mislead you. Maybe something like this. Maybe we have something like this, where I know that this point down here is going to be a point of interest, and this point up here is going to be a point of interest. So now, this point at the end point is not an absolute maximum, right? It's not absolutely bigger than every other point in this picture. It's just a relative endpoint maximum. Why is it a relative maximum? Because relative to the points around it, it's bigger, right? This is taller than the other points around it. It's higher than the other points around it. So relative to the points around it, it's a maximum. This point up here is the highest point in this whole picture. This is the absolute interior maximum. It's an absolute maximum. So absolute max and mins don't have to appear at endpoints. You can have any kind of picture going on. There don't even have to be absolute max and mins. You don't have to have any kind of max or min for your function. This one, though, does have, what does it have here? This is a relative, no, this is an absolute. This is the lowest point. So this is an absolute interior minimum. And this point here would be a relative minimum, relative endpoint minimum. So when you're thinking about classifying relative mins and max, you just look at the points around. See, notice how in this picture, this endpoint here is a relative minimum, but it's higher than the relative maximum, right? We're having this weird situation, which is fine because with relative max and mins, we're just looking at the picture zoomed in right there, right around that point. So we can have weird things happening like this where the relative maximum is lower than the relative minimum. All right, one more example with an unbounded domain. Let's say we have some function where only one side of the domain has been restricted. So we've got a point of interest down here somewhere, the lowest point on this whole graph. We've got this endpoint over here. This would be a relative maximum because relative to the points around it, it's higher. So it's a relative maximum. This point is the lowest point on this entire graph. This graph never turns around and comes back down. So we have an absolute minimum I'll say absolute interior minimum. And that's it. There is no absolute maximum in this picture because the function is unbounded. It goes up to infinity. Oops. It's unbounded. So there is going to be no absolutely highest value for this function. Okay, so now I just want to review how we can find potential extrema, right? Potential being the key word here. Not every one of these points that we find will necessarily be an extreme value, but they will be potentials. It will be candidates for being extreme values. We've got endpoints. You can have extreme values at endpoints. So if you've got some function and the domain has been restricted to some interval, then you will have endpoints, and you could potentially have extreme values there. Extreme values being a max or a min, absolute or relative. We've got I'll say flat places, right, in the curve where like the curve flattens out right there, right? If a curve is flattening out, then we have potentially a highest value there or a lowest value there. And how do we check this? This is where we set the derivative equal to 0, right? Because the derivative in a geometrical sense is the slope of the tangent line of this curve. And what happens when a curve flattens out? The slope of its tangent line, is 0. So the slope of the tangent line is 0 at this flat place where we may or may not have a max or a min. So the way we're going to find these flat places is we're going to set derivative. You have to take a derivative of whatever the function is, set derivative equal to 0, and solve. Solve for x or t or whatever the input variable is. The last way, which is one that we haven't seen a lot of, God, I'm already out of room, is at cusps, points like this or this, these points. We can have extreme values there at points. When I say points, I mean like pointy bits of the curve. We call them cusps. And these occur when the derivative is undefined. These occur when the derivative is undefined. So let's run some examples of finding potential extrema. Then we're going to talk about the tests that we have to see what kind of extrema we have, so classifying extrema values. So let's see if I can come up with an example that has all three endpoints, flat places, and cusps. Okay, I've got an example. Okay. This function will have, it obviously has endpoints that need to be checked. We can see that by this bounded domain here. It's also going to have a spot where the derivative is 0. In other words, it's going to have a flat spot in this domain. And it's also going to have a cusp in this domain. So we're going to see how all three of these work out algebraically. And then at the end, I'll graph a picture of this to help us classify the extrema. So first, endpoints. all we have to do here is find the functional value, the y value, at these endpoints. So f of negative 2 is negative 2 to the 2/3 plus negative 2. That's going to be, let's see, negative 2 squared and then cube rooted, so cube root of 4 minus 2, and we'll leave it just like that. So negative 2 to the 2/3, remember negative 2 to the 2/3 means cube root of negative 2 squared. So that's how I got cube root of 4, because negative 2 squared is 4. I'm going to leave it just like that. Or actually, let's see, can we get a approximation? Okay, so I got approximately negative 0.4 for this endpoint. F of 2 is going to be 2 to the 2/3 plus 2. So it's going to work out very similar. 2 to the 2/3 will be the same as negative 2 to the 2/3. So I'm getting cube root of 4 plus 2, which will be 4.4. No, 3.6, which is approximately 3.6. Okay, so we have our endpoints. Now, since this took up a lot of room, I'm going to write our endpoints over here. Coordinate point negative 2, where is it? Negative 2, comma, negative 0.4, and 2, comma, 3.6. That's all we have to do for our endpoints. That's all we have to do for our endpoints. Just find out what the y value is at the endpoint, write them down. We're going to compare them to the other potential extreme values later. Okay, now let's set our function equal to 0, or our derivative equal to 0, so we can find those flat points where the slope of the tangent line is 0. So f prime of x, I'm going to use the power rule here. I encourage you to stop the video and try to take the derivative of this by yourself. If you do, you should get 2/3 x to the negative 1/3 plus 1. Okay. Now what I want to do is set this equal to 0 and solve for x if possible. I want to solve this for x. I'm going to, again, I encourage you to try this algebra on your own. This would be a good exercise. So, let's see. I'll subtract 1 from both sides. Then I'll multiply by 3/2 to get rid of the 2/3. So x to the negative 1/3 is equal to negative 3/2. So that got rid of the 2/3 here. And it's negative because this 1 was negative. And now what have I got here? This is the same as 1 over cube root of x equals negative 3/2, because x to the negative 1/3 is the same as 1 over cube root of x. I'm trying to solve for x here. So how about I multiply by cube root of x on both sides, so that I'll have 1 is equal to negative 3/2 times the cube root of x. Send this back across the equal sign to get negative 2/3 equals cube root of x. So multiplying by 2/3 there. Maybe this wasn't the most efficient way of solving this, but that's fine. And now, to get rid of the cube root, I'm going to cube both sides. So I'm getting negative 2 over 3 all cubed is equal to x, which will be negative 8 over 27, negative 8 over 27, which is approximately 0.3. Okay. So quite a bit of heavy algebra here in solving for that flat point in the graph. Okay. So when this function, when this derivative is equal to 0, I'm getting that x is approximately 0.3. Okay, so I think I dropped the negative sign back here somewhere. It should have been, it was x equals -8 over 27, which is approximately negative 0.3. I think I may have left off the minus sign earlier. There it is now. What I want is I want to add this point to my list of potential extrema over here. So the x value is approximately negative 0.3, or I could write it as 8 over 27. I need some y value now. Well, how do I get a y value for my function? I just plug this back in to the function. So I'll say f of, now when I'm plugging in here, I don't want to use the approximate value. I want to use the exact value. So f of -8 over 27 is going to be -8 over 27. This isn't going to be as bad as it looks. Raised to the 2/3 plus -8 over 27. Okay, this is not as bad as it looks because both of these numbers are perfect cubes, 8 and 27, and -8 over 27 raised to the 2/3 is the same as -8 over 27 all squared and cube rooted, and then plus, still have that plus -8 over 27 hanging out at the back. That was because of the plus x here. So what I can do now is I can take the cube root of both of these numbers and then square them. That's fine. I can do it in that order. So I'll have cube root of -8 is -2. Cube root of 27 is 3. I'll still need to square them. And then plus -8 over 27. So this isn't going to be nearly as bad as it looked back here because they both ended up being perfect cubes. So I'm going to have 4 over 9 plus, I can say instead of plus negative, I'll just say -8 over 27. And then common denominator, 12 over 27, multiplying both of these by 3, -8 over 27, and finally, I'm getting, can you see that? Barely. 4 over 27 for my y value. 4 over 27 for the y value. Which, since we're going to be comparing these y values later, maybe it would be better to approximate 4 over 27 so we know what it is as a decimal. So let's write this point as approximately -0.3 was the x value, and 4 over 27 is roughly 0.1. Okay, so this is the same coordinate point. I'm just approximating it here. I'm just approximating it because we all have an easier time picturing where this number is on a graph as opposed to where this number is. Okay. I'm still not done finding my list of potential extrema though. I've done my endpoints, not really a whole lot to those, just plug each one of them into the function, write them down. This endpoint, or this extreme potential value is a bit more of a process. Have to take a derivative, set the derivative equal to 0, solve that equation for x, then take that x value, plug it back into the original equation to get that y value. And now here I am with this new potential extreme value. Now the next thing to check is where is this, if it is undefined, where is the derivative undefined? Where is the derivative undefined? Is it undefined anywhere? The examples we've done in class have not had any undefined spots in their derivatives because we've mostly been dealing with polynomials. So where is the derivative going to be undefined? Well, because there is an undefined spot in this derivative. Note that the derivative can be rewritten as 2/3 times 1 over cube root of x plus 1, right? Because that's what x to the negative 1/3 is. It's 1 over cube root of x. So x cannot be 0 here. Because if x was 0, I'd have 1 over cube root of 0. I'd have 1 over 0. That's not allowed. 1 over cube root of 0 is 1 over 0. That's not allowed. So my derivative is undefined. Excuse me. Is undefined at that position. What is the functional value at x equals 0? Because this is what I want now. If I know my derivative is undefined there, that means I have a cusp at 0. So let me find what the y value is at that cusp. What is, I'll say, the functional value, the original function. So obviously, I'm not asking you to plug 0 into the derivative because I'm telling you x cannot be 0 in the derivative. But I'm asking you what can x, what does 0 give you in the original function? F of 0 is going to be 0 to the 2/3, which is just 0, plus 0. Okay. So that was nice and easy, at least in the computation here. That's a new critical value, or a new potential extreme value. So we've got 4. We've got our 2 endpoints, we've got a flat place, and then we've got a cusp. Okay. Now, based off of the y values here, all of these y values, we could classify these as absolute max or absolute min, but to classify the relative max and mins, we really want to get a picture or do some test points now to be more careful about which one of these are relative and which ones are absolute. So, okay, so the next step is going to be classifying these as absolute max or min and relative max or min. So I'm going to write our example problem and all of these potential values off on the side. I'm going to talk about the first derivative test for a bit, and then we'll use the first derivative test to classify these points. Okay, so let's talk about classifying potential extrema now. Really, the best thing here, the best thing you can have is a graph. If you have a graph, all you have to do is look at it and point to where the absolute and relative max or min are, just like I did at the very beginning with those pictures I drew. If you have a picture, classifying these becomes super easy, at least relative to the tests that you have to do if you don't have a graph. So first, let's look at the situation where you don't have a graph. In class, what we've done is we've tested the points by plugging in numbers around the point and seeing if they were higher or lower, and that was a lot of work. It was a lot of computation, and we have, for our example, we have 4 potential extremas. We're going to have to check around each one of those points. It's a lot of work. So let me show you a slightly better test. Called the first derivative test. It's pretty intuitive. Basically, what it says is it's a test for testing if a point is a maximum or a minimum, and it tells you whether, or it tells you that by looking at the sign of the derivative on either side of the point. It says if the derivative is negative about what a negative derivative means. A negative derivative means the graph is pointing down, right? The slope of the tangent line is negative. If the derivative is negative on the left of a point, so we're going to be checking some coordinate points. So if the derivative is negative on the left, so it's like this, if it's negative pointing down on the left and positive on the right, what do we have? So if it's positive on the right, that means it was negative on the left, and then on the right it's pointing up, like that. Then we have a minimum. See why? It's negative and then positive, then that value must be a minimum. It doesn't tell you if it's absolute or relative, it just tells you that it's a minimum. Similarly, if the derivative is positive on the left and negative on the right, then we have a maximum. Okay, so this is the corresponding statement for if the derivative is positive on the left of the point and negative on the right, then we have a maximum at that point. So if it's positive on the left, so the slope of the tangent line is going up, positive on the left of the point, and then negative on the other side of this point of interest, then that point is a maximum. So it should seem like it's a pretty intuitive test. And why is it better? Because we're still going to have to test points on either side of every single one of our potential values. We're still going to have to test points on either side. But it's a little bit faster because we don't actually have to compute the point itself and compare it to, we don't have to actually compute the y value itself and then compare. All we have to do is just find the sign of the point of that y value, and that's enough. That's all we need is the sign of it. So this makes the computation a little bit faster. So let me write down that function that we had. We had f of x equals x to the 2/3 plus x, where f prime. So the first derivative test does not use the function to test the points. It uses the derivative. That's why it's called a derivative test. And the derivative was 2/3 times 1 over the cube root of x plus 1. And the points we have are this one, let's see, this one, this one, okay, so we've got these 4 points to check. What we want to do is check points around each one of these x values at -2, 0, -0.3, and 2, and see what the sign of the derivative is on either side of these points. Okay, so a good strategy here, make a table. Let's say x and not f of x, but f prime, right? That's f prime of x. So in here, I'm going to be writing the sign of the derivative. How many of these am I going to need? My lowest x value is -2. Then I've got the -0.3, so I'm leaving a gap in between each one because I need to test the points around -2, then around -0.3. The next one is going to be 0, and then the last one will be 2. So I'm going to check some x value here and here, find the sign of the derivative, and then these two, and these two. Okay. So a good x value over here, well, actually,